Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 11 on stoichiometry, and we are covering 11.3, limiting reactants or limiting reagents. So just a review of what we covered last week. Suppose you wanted to make 2 ham and cheese sandwiches that takes 4 slices of bread, 4 slices of ham, 2 slices of cheese. You can make 2 ham and cheese sandwiches. If you only have 1 piece of cheese, you cannot make 2 ham and cheese sandwiches, so cheese is your limiting factor. So usually during a chemical reaction, one reactant is limited and there's an excess of the other reactants. And the limited reactant determines how much product is made, and it's not necessarily the reactant with the smallest amount. For example, if you have 10 grams of hydrogen and 20 grams of oxygen, the oxygen will actually run out first. So the hydrogen would be the excess reactant, and that is, there will be some hydrogen left over after the chemical reaction is complete. And we've been working on limiting reactant problems. So first off, as always, we write a balanced chemical equation. We convert each reactant from mass to moles and label the answer have. And for each reactant, we pretend it all reacts. We figure out how much of the second reactant would be needed and label the answer need. Then we compare the calculated amount of each reactant with the actual amount of each reactant. And if the actual amount, or have, is less than our calculated amount, our need, that one is our limiting reactant. And we started practicing this. Given 3 moles of solid iron and 4 moles of water vapor, it will react to form 1 mole of black iron oxide, which is solid, and 4 moles of hydrogen gas. So given we have 36 grams of water, that reacts with 167 grams of iron and produces black iron oxide. Which reactant is the limiting reactant? And we have already figured that out. We wrote down what we knew, 36 grams of water, 167 grams of iron. We're calculating the limiting reactant. Our balanced chemical equation was given to us. We took the amount of water and converted it into moles, and that is the moles of water we have, 2.00. And we did the same thing with iron. We have 2.99 moles of iron. And then we need to do our limiting reactant problem. We took our 2 moles of water and pretended it all reacted by doing a mole ratio between iron and water, and we would need 1.5 moles of iron. And then we compared that to having 2.99. So we have more than we need, so iron is in excess. And then we did the same thing with iron, 2.99 moles of iron, and we did a mole to mole problem. If all of that reacted, we would need 3.99 moles of water, which as you can see, we only have 2. So we have less than we need, so water is our limiting reactant. So then we compared them, and we know that we have less water than we need, so that is our limiting reactant. And we went through a check of it, and that all seemed reasonable. We also answered how much of the excess reactant was used. So if we go back up to our problem up here, we know that if all of our limiting reactant reacts, we're going to use 1.5 moles of iron, and that is what we have. 1.5 moles of iron will react. And now to find the amount of product formed, you must use the limiting reactant, which is a mole to mass problem. So our C part of the question up above was, what is the mass of the product black iron oxide? Okay, I'm going to be writing on the board, so you won't be able to see me, but you'll be able to see what I'm writing on the board and hear me. Okay, you know that we have 2.00 moles of water, and we're trying to find the number of grams of black iron oxide, which is Fe3O4. Fe3O4. So then we're going to set up our problem and calculate. So we know that we have 2.00 moles of water over 1 times our mole ratio of moles of water over moles of black iron oxide, Fe3O4, and we get that from our balanced chemical equation, which is way up here, and that's going to be 4 moles of water and 1 mole of black iron oxide. 1 mole of water and 4 moles of black iron oxide. Just checking to see that you're awake. 1 mole of black iron oxide and 4 moles of water times our molar mass, which is 1 mole of black iron oxide over 231.55 grams black iron oxide, and equals, so double check that we got this right, moles water, moles black iron oxide, moles black iron oxide, and I'm left with grams of Fe3O4, black iron oxide. I take 2 times 231.55 and divide it by 4 to get an answer of 115.8 grams Fe3O4. And if we look, we get 3 sig figs, so that equals 116 grams of Fe3O4. Okay, and then we're going to do a check. So we have 2 moles of water, and if we have 1 mole of iron oxide, for every 4 moles of water, we'd have about a half a mole of black iron oxide. And we know each mole of black iron oxide is about 230 grams. So if I have a half of a mole, it would be about 115 grams. So we did a good job. So good job. And before moving on from a limiting reactant problem where we were looking for the product, we should make sure that we used the limiting reactant to calculate the product. So we go back up, and water was indeed the limiting reactant. So we're good to go. So let's look at this image, which can also be found in your book. So if we have before, in a chemical reaction, we have reactant A and we have reactant B, and nothing's happened yet, but then a chemical reaction occurs and we used up all of reactant B, so that was our limiting reactant, and we have some of A left over, so that was our excess reactant, and we made a bunch of product. Okay, in your book is a great visual for limiting reactant problems. So the first step is to convert both reactant masses into moles, and this gives you the amount you have available to use, and that's your have. The next step, you multiply each reactant, the number of moles of each reactant, by your mole ratio from your equation, from the balanced chemical equation, to find out how much reactant is needed. If the first reactant was all used up, how much of the second reactant you would need. So this gives you the amount you need to consume all of the reactant. Then you compare the amounts of the reactants. Compare what you have to what you need, and if what you need is more than what you have, it is the limiting reactant. Or in other words, if you have less than you need, that is the limiting reactant. And here's another nice visual found on that page. So we take our grams of reactant and we divide by the molar mass to make it moles of reactant. And then we use our mole ratio between the reactants to determine the limiting reactant. And then we take our limiting reactant and use a mole ratio with the limiting reactant and the product to figure out your moles of product. And then we multiply the moles of the product by the molar mass of the product to get our grams of product. So that will tell us how much product we have. So basically that is how we go from mass of our limiting reactant to mass of our product. Okay, so moving on, the Haber-Bosch process was developed in World War I to make ammonia to be used for explosives, and it is now used for fertilizers. Perhaps you remember Hank Green talking to us about this, how he was a brilliant scientist and got the Nobel Prize, and also a war criminal in the same scientist in his lifetime. So complicated socio-political stuff. So making ammonia using the Haber-Bosch process uses a lot of energy and it can be expensive. So worldwide, the consumption of fertilizer is about 150 to 200 million tons. So I'd like you to think about the consequence for the environment and underdeveloped countries if it uses a lot of energy and it can be expensive. Now comes the interactive part. You try. Please write this down just like normal. 100 grams of nitrogen reacts with 10 grams of hydrogen. Which reactant will limit the amount of ammonia produced? And how much ammonia can be produced? So what I need you to do in your notebooks is to set up this limiting reactant problem just like we did the other one, and figure out first the limiting reactant and then use the limiting reactant to figure out the product. Okay, what did you get for your balanced chemical equation? Did you get that? And then the next step is to figure out how many moles of each reactant you have. So what did you get for those? Did you get 3.57 moles of nitrogen, which we label as have, and 4.95 moles of hydrogen, which we label as have? The next step is to figure out if all of reactant A reacted, how much of reactant B would be needed. So if all of the nitrogen reacted, we would need 10.7 moles of hydrogen, and we label that need. If all of the hydrogen reacted, we would need 1.65 moles of nitrogen, which is our need. Then we need to figure out the limiting reactant. As you can see, we have 3.57 moles of nitrogen, and we only need 1.65 moles, so that's in excess. We have 4.95 moles, but we would need 10.7, so we don't have enough of that. So water is our limiting reactant. And by water, I mean hydrogen. Hydrogen is our limiting reactant. The B part was figuring out how much product would be made. So you do need to make sure you use the hydrogen. So we set up the moles of hydrogen, do a mole ratio, times by our molar mass of ammonia to get 56 grams of ammonia. So we would be able to make 56 grams of ammonia. And then finally, you should check if it makes sense. We did figure out how much ammonia could be produced, and we did figure out which reactant would be the limiting reactant. And let's see if we got a reasonable answer. If we start out with 10 grams of hydrogen, and each mole is about 2 grams, we would have about 5 moles of hydrogen. And for every 3 moles, you get 2 moles of ammonia. So if we have 5 moles of hydrogen, times 2 is 10, divided by 3 is about 3. So we'd have about 3 moles of ammonia. And each mole is about 17 grams, so I'll round that to 20, which is 3 times 60 is about 60 grams. And we got roughly 60 grams, so we got a reasonable answer. Good job. Our next video will be covering 11.5, solving stoichiometric problems. See you then.